Stanford University.
We were waist deep into into the Dirac land, the Dirac Sea. Well, we didn't get to the Dirac Sea yet. But before we continue with the three-dimensional, I'll do a little review of the Dirac equation that we studied, and then we'll go into the three-dimensional version, three space, one time dimension, as a real world Dirac equation. But before we do, let's go back and review generalize what we said about second quantization, the field theory, the fields governing multiple particle systems. We made them out of creation and annihilation operators. What's the difference between fermions and bosons in that respect? And the difference is simple, not so intuitive, but rather straightforward. If you have two bosons, you can put them into the same state, number one. And no problem putting them into the same state. And what's more, the creation and annihilation operators all commute with each other. Nothing particularly odd about things which commute with each other. There is something very odd about things which anti-commute with each other. So let's talk about anti-commutation. Supposing we have two particles and we want to say that when we interchange them, that the wave function or the state vector should change sign. So let's think about what that would mean for these operators that we're constructing. A particle at x and another particle at y. Particle 1 now stands for which slot? This is slot 1, this is slot 2. This stands for particle 1, this stands for particle 2. X stands for the position of particle 1, y stands for the position of particle 2. Neither x nor y refers to the x and y coordinates. X and y are each, if you like, three-dimensional positions or one-dimensional positions depending on the context. That's a state with two particles, one at x and one at y. For bosons, this is exactly the same thing as putting particle 1 at position y and particle 2 at position x. They're equal to each other. Okay? So in particular, that would tell you, how do you make a particle at x and particle y? You take psi of x times psi of y, this should be creation operators. A creation operator for a particle at x, a particle at y, and you hammer on the vacuum. You let them act on the vacuum, and that creates particle at x and y. Supposing I want to interchange particle x or the two particles. That's just interchanging x and y. That would be psi dagger at y, psi dagger at x, also vacuum. Good. Now, why is this true? It's true because the psi's commute with each other. You can interchange them. This and this are related very simply by interchanging the two operators here. And if they commute, that just says that psi dagger of x times psi dagger of y is the same as psi dagger of y times psi dagger of x. And so it's guaranteed that with the objects and the theories that we've been making up till now, that they satisfy this kind of Bose statistics, this kind of boson rules. Now, for fermions, the rule is exactly the same, but with a minus sign. Remember that the state vector of a system, the real physical observable state vector of a system, doesn't care about the sign here, but in keeping track of the formulas, it's important to know that for fermions, if you interchange the two particles, you get a minus sign. That must mean that for fermions, if psi here is representing fermions, that this is the top equation here, the top formula, is minus the bottom formula. And the mathematics that goes with this is just a statement that for fermions, the fields anti-commute. So let's write out what that means. It means psi dagger of x times psi dagger of y equals minus this over here, but let's shift it to the left-hand side and write that plus psi dagger of y psi dagger of x equals 0. This object, if you take two operators and you take their product, and instead of subtracting in the opposite order, you add in the opposite order, that's called the anticommutator. And it's written, instead of a square bracket, instead of a square commutator, usually written with a curly bracket, psi dagger of x, psi dagger of y equals 0. Okay. In general, when you go from fermions to bosons, you just take every commutation relation and replace it by an anti-commutation relation. And that's how you go from fermions to bosons. Now that has, let's see, is there anything else? Yeah. First of all, it's quite clear that you can't have two particles in the same state. For example, supposing you wanted to put two particles at the same point. You want to put two particles at the same point. That corresponds to let's get rid of this over here. That corresponds to acting with creation operators at the same point. But this equation over here, or let's say this one over here, that tells us that psi dagger of x times psi of x, psi dagger of x, plus psi dagger of x times psi dagger of x. That's the anticommutator of psi dagger x with itself. I've just replaced y by x, and the statement here is that that should be equal to 0. Well, this operator and this operator are exactly the same. This is just twice psi dagger of x times psi dagger of x equals 0. And if twice something is equal to 0, the thing itself is equal to 0. So trying to put two particles into the same state always gives you 0. Anticommutators give you fermions, which cannot go in the same state. There's an interesting peculiarity here. For bosons, there's a clear mathematical distinction between creation operators and annihilation operators. Even if you didn't know what the devil these things stood for, when you write out the commutation, we have no idea what these things stand for. We just know that there's this algebraic structure that some kind of creation of some sort of object. Let's not put daggers on for now. It doesn't matter, daggers or no daggers. Some sort of objects commute. These things commute. No, I'm sorry. I wanted to take psi dagger equals 1. Here we are. This way. Equals 1. That's a harmonic oscillator. Or it could just be a creation and annihilation operator for a boson. Okay? Could you mistake which one is the boson operator, which one is the creation operator, and which one is the annihilation operator? Well, if you try to switch them, if you try to replace A by a dagger, and A dagger by A, this is very definitely not equal to 1. In fact, what is it equal to? -1, right? commutator, if you switch the two things, the commutator changes. This is -1. And you could always tell, even if I didn't label these as A and A dagger, if I just labeled them as A and B and asked you which one is the creation operator and which one is the annihilation operator, what you do is you look at the commutators, and if the commutator is +1, then the first one here is the creation operator and the second one is the annihilation operator. There's no way to make a mistake. And in fact, creation operators and annihilation operators are fundamentally different. Here's the stack of all possible states. N equals 0, n equals 1, n equals 2. Creation operators, just mathematically, creation operators do not annihilate any state. They just take you up the ladder. And since the ladder never ends, a creation operator never runs into the problem that an annihilation operator does if it annihilates too many times. Annihilation operators, when they get down to the bottom, they give 0. Another way to say it is that this spectrum of n going from 0 to infinity is not the same if you turn it upside down. You can go up to infinity, but you can't go down past 0. Okay, what about fermions? Well, now you look at the fermion operators. They also have creation and annihilation operators. The difference, though, is that you have anti-commutation relations for fermions. You also have creation operators. You can create a fermion +1. Anti-commutators are the same if you interchange. Why? Because this is A dagger plus A dagger A. It doesn't matter which order they're in. So just from the mathematical structure, from the algebra, there's no difference between creation operators. They do different, it's true, they do different things, but just looking at the algebra of them, you can't tell the creation operators from the annihilation operators. And another way of seeing that is just to look at the possible occupation numbers of a fermion. Let's say it's a fermion with only one state. Fermion is in the ground state of the hydrogen atom. Okay? What can you have? The answer is you either have no particle or you have one particle. You can't have any more than one, and you can't have any fewer than 0. What does the creation operator do? It takes you from 0 to 1. But what does it do when it hits 1? No state there. Annihilates the state, right, 0. On the other hand, the annihilation operator takes you down. If there's a particle there, sure enough, it can take you down, but if there's no particle there, end of story, you annihilate the state. So there's a complete symmetry between being empty and being filled, and replace creation operators by annihilation operators. Now that doesn't mean they're physically the same. It just means the algebra and the mathematics, the symbols, you can't tell one from the other. Yes, question?
I had a question back when you were saying if you try to have two fermions in the same place, you'd have side dagger, x equals 0. Why is that a contradiction, or why is that?
It's not a contradiction. It just gives 0. It doesn't give a state. A 0 state is nothing.
So, but that I'm just curious. That operator squared essentially, right?
Side dagger is squared. Yeah.
Yeah. If you have an operator squared, does that mean the operator is 0?
No, it means the operator squared is 0.
Okay.
No. Here, look. Here's a creation operator. The creation operator squared, there's nothing up here for it to give. So it gives 0. If you take the creation for fermion. For fermion, if you take the creation operator squared, it's 0. There's nobody here. If you take the annihilation operator squared, it's 0. On the other hand, for bosons, there is not this symmetry of filled and empty. It's the symmetry of filled and empty. two possible states, and only two possible states, and no, for a single state of a fermion. All right, that's going to play a role. We'll get back to it. What it says is that in some sense, just pure mathematical sense, you can interchange for creation and annihilation operators. Now, you may not want to do that because they have physical significance, but just as the algebraic structure of them, you can interchange them. Okay, let's come back now to the Dirac equation, the wonderful Dirac equation. And let's pursue it. Various things we want to understand. We already figured out how to deal with the fact that the simplest Dirac equation that we wrote down doesn't have the possibility of having a mass. Let's just go back through it. The simplest thing was just to write an equation which was d by dt of psi, let's put an I there, I psi equals minus I d by dx psi. This was for the case of one dimension. Now this psi here is let's say a wave function for a single particle. For the moment, we're just doing single particles, one particle. This would be the Schrodinger equation for this would be the Hamiltonian over here. This would be the Hamiltonian acting on psi is equal to the momentum acting on psi. And we would recognize this as just a theory in which the energy of a particle is equal to its momentum. Okay. Energy equal momentum is a relativistic massless particle. For mass, you want E squared equals P squared plus M squared. All right, so this was a failure as a theory of one-dimensional electrons because one-dimensional electrons moving on a wire or something have a mass. Okay, we figured out what to do with that. We introduce a second species of electrons, which these were right-moving electrons. These were waves which moved strictly to the right. The time derivative is minus their space derivative. That means they move to the right. So wave packets just propagate off with constant velocity, speed of light. Okay. What you want to do is you want to invent another species which propagates to the left. So we could call this one psi 1, and we invent another one, h psi 2, a completely different particle, equals minus p psi 2. A particle whose energy is minus the momentum. And this just interchanges plus momentum in that direction, right, with minus momentum in that direction. And so this particle clearly propagates to the left. Then we combined these two equations by taking psi 1 and psi 2 and making a column vector out of them. Quantum mechanically, this means the particle can either be of one type or the second type. So there's a new degree of freedom we discovered, we were inventing a new degree of freedom, which is above and beyond the momentum of the particle. It's its handedness. Does it move to the right or does it move to the left? Incidentally, this particle can have negative energy or positive energy because P can be positive or negative, but in either case, it goes to the right. This one can have positive energy or negative energy. In either case, it goes to the left. Okay, then we invented a matrix. The matrix was alpha, oops, that's gamma. Lie down, alpha. Get on your side and be alpha. And this says that psi 1 is an eigenvector of alpha with eigenvalue plus 1, and psi 2 is an eigenvector of alpha with minus 1. And now we can combine these two equations and just write that h psi this is supposed to be a simple psi. H psi is equal to alpha times p psi. What does this mean? This means that if alpha is plus 1, h is p. If alpha is minus 1, h is minus p. So we have both of them in the same structure here at the cost of doubling the number of components of the field. Okay. That didn't get us a mass, but at least got us things going in both directions. Then we did one more trick. We invented another matrix that's called beta, and that one looks like this, 1, 1. Now the fact that these happen to be Pauli matrices is somewhat incidental at this point. They're just matrices for the moment. And instead of writing h is equal to alpha p, h is equal to alpha p, that's that equation down there, plus p or minus p, depending on the sign of alpha, we added another term, beta times m. Okay, now here's some things about alpha and beta. Alpha squared and beta squared are 1. And alpha beta plus beta alpha equals 0. You can check that. Just check that if you multiply them in one order, you get one thing. If you multiply them in the other order, you get the other thing, and they cancel. You might say that alpha and beta anti-commute, and it's true, but don't confuse that with the anti-commutation of the fields. Okay, so alpha and beta anti-commute, they each square to 1. Now, consider h squared. That's the square of the energy. That's the operator that governs the square of the energy. Well, that's going to have one term, which is alpha squared p squared, another term, which is beta squared m squared, and then yet another term, which is alpha beta plus beta alpha p times m. But we were lucky. Alpha beta times beta alpha is identically equal to 0, and so the only terms that are there are p squared plus m squared, which is exactly what we want for a relativistic particle with mass. Okay, so we managed by combining a left moving and a right moving, and then coupling the left moving and the right moving through this matrix beta. The matrix beta does couple them together. We end up with a particle with a mass. It's in this sense that a mass term is a mass term in the Hamiltonian is something which sort of switches you from left moving to right moving. Well, it doesn't really do that. It just gives the particle a mass, but you can picture it as causing transitions between left and right, moving to the left and moving to the right. And if you can have transitions between left and right, you might start to think, well, maybe it even makes sense to think of a particle at rest. Sort of at rest. At rest, good. You can have a massive particle at rest. You can't have a massless particle. What are you doing?
I'm filming it.
Oh, okay.
But question, is there more to the physical interpretation of having both types of particles?
It is what it is. Is there more to it? We'll get there. Yeah, there is more to it, but at this point, that's all there is, yeah. Sometimes things are just abstract. Sometimes that's all there is to it. All right, so then comes the question, how do we do this in 3 dimensions? 3 dimensions instead of 1 dimension, 3 dimensions of space. Okay, so let's go back. Let's start with what will turn out to be the case which is massless. Will turn out to be a case which can't have a mass. Here's what we're going to do. We have 3 dimensions of space. It wouldn't make sense to have only one alpha. We can have px, we can have py, and we can have pz. This looks like it wants to be some sort of product of a degree of freedom with p, but p is a vector. What do we get to make? What do we get to multiply by vectors to make things which are invariant? Other vectors. We take dot products of vectors. So here's what Dirac thought to himself. He thought this alpha here must be a vector if we're going to multiply it by p and make something which is rotationally invariant. That means it must have three components. It must have three components. So he said, let's try the equation h equals alpha dot p. This means alpha sub x px plus alpha sub y py plus alpha sub z pz. Okay. What do the alphas have to do to make this sensible? For the moment, we're not going to try to make a mass. We're going to make a massless equation. So what is the right formula for our massless particle, its energy versus momentum? The answer is energy squared equals momentum squared, but that means energy squared equals px squared plus py squared plus pz squared. That's what we want to get. H squared equals px squared plus py squared plus pz squared. What happens if we square this thing over here? Well, we'll get terms which are alpha x squared times px squared. That's okay. That just means we want alpha x squared to equal 1. Likewise with alpha y. Alpha z squared equals 1. But now we want to make sure the cross terms aren't there. When we multiply out the cross terms, we get px times py, and it will multiply alpha x alpha y plus alpha y alpha x. That's what will happen. So we had better have that alpha x alpha y plus alpha y alpha x equals 0. And likewise for the other combinations. Same with x and z, same with y and z. So Dirac says, can I find three matrices which each one squared is 1 and which mutually anticommute? And the answer to that's easy. Pauli matrices. The three Pauli matrices do exactly that. Okay? So if we say alpha x is equal to sigma x, the Pauli matrix equals 1, 1, 0, 0. Alpha y equals sigma y equals what? Minus I, O, O. And finally, the last one is alpha z equals sigma z, and that's the easy one to remember, 1 minus 1. And we got it. In other words, our Hamiltonian H is equal to sigma dot p. You can think of this as a particle whose, well, it's a particle that has a spin, that's the sigma, and a particle and it has a momentum, and the energy is proportional to the dot product or the component of spin along the direction of motion. Okay? Good. So it's a massless particle, but it has the odd behavior that its spin is always, well, let's go back. Okay. Sigma dot p. Its energy is proportional to the component of its spin along the momentum direction. Now, the component of a spin is always plus or minus 1. So it sounds like there are two cases here. One case where the spin is literally along the momentum, pointing along the momentum, and the other case in which the spin is opposite to the momentum. In one case, the energy is positive. If sigma is in the same direction as the momentum, sigma dot p is positive. If they're oppositely aligned, that's negative. So again, we have the situation, massless particle, okay, a massless particle with positive and negative energy states, and instead of saying that the particle can just move along the x-axis or along the y-axis, sorry, along the x-axis positively, along the x-axis positive, this one is stuck in a different kind of way. It's stuck in that its momentum or its energy is sigma dot p. In other words, if its energy is positive in particular, if it's a positive energy particle, then its spin is always locked to be in the same direction as the momentum.
So I've heard said that somehow the spin drops out of the Dirac equation, so to speak.
It does?
Well, I've heard that said, maybe that's wrong. I was going to say,
That's
this
wrong?
seems to be we're introducing it.
Well, it certainly doesn't drop out of the Dirac equation.
Where does it come from?
What do you mean, where does it come from?
I mean, we just introduce it because we know the electron has a magnetic moment.
Well, that's not why Dirac introduced it. Dirac introduced it because he wanted to write a Hamiltonian equation.
I think you're misreading it. It falls out. It comes in as a result of.
Oh, falls out means that it just plopped into your lap.
No, I mean it the way Mike said.
Which?
That it comes as a result of.
Yeah, it comes as a result of. Plops into your lap for free. Right. I thought you meant it falls out, that it doesn't appear in the equation.
No.
Yeah.
That would be drops it.
Ah, okay. Good.
A couple different levers.
Right. Yeah. Well, okay. Look, Dirac's logic, which was not necessarily unimpeachable, was that he wanted to write an equation where the Hamiltonian would be written in terms of the momentum without having some insane square root. This is the best he could do. He said, I'll write h equals alpha dot p because I want it to be linear in the momentum. But then he said, what the hell is alpha? It can't just be a bunch of numbers. And by requiring that h squared equals p squared, he found the Dirac matrices, or these he found the Pauli matrices. So he said, ooh, I think I've discovered why they spin. And in fact, he was right in a sense. He was not right that every particle on Earth has to have a spin. But he was right that the particles that are described by the Dirac equation have a spin, and that meant fermions. Okay, so far we haven't said what this has to do with whether they're fermions or bosons, and we'll come to that. Okay, but still we have h squared equals p squared, and we don't have a mass. H squared equals p squared is the massless particle. What do we have to do? So you might think, well, what we have to do is put another beta m here. Let's try that. What are we going to require? When we square h, we're going to get the usual sigma square p squared, which is just p squared. We're going to get, assuming the square of beta is 1 again, let's assume beta squared is 1 again. Then we'll get an m squared term. We'll get h squared equals p squared plus m squared. Plus a cross term. And the cross term will involve things like, let's say, pxm. I take the x component of this, and I multiply it by sigma x beta plus beta sigma x. In other words, we want this to be, of course, 0. We don't want that there. So we want whatever beta is to anti-commute with all the Pauli matrices. That would be great, except that there is no matrix which anti-commutes with all the Pauli matrices. When you start looking at 2x2 matrices, you discover that there are 3 mutually anti-commuting ones and no more. So we give up. Or we say, why does it have to be 2x2 matrices? Maybe what we have to do is introduce another binary degree of freedom, another 2-value degree of freedom. So if there's this 2-value degree of freedom and another one, we would be talking about 4x4 matrices. Each particle would have a 4-component thing associated with it, some new degree of freedom. Well, you could look for 10x10, you could look for 100x100. Turns out you could look for 3x3. There are none. No 3x3 matrices which have the anti-commutation relations of the 4 necessary matrices here. The first case where you discover that there are 4 mutually anti-commuting matrices is the 4x4 case. Now, the fact that it's 4x4 has nothing to do with the fact that space-time is four-dimensional. It's just a mathematical fact about anti-commuting matrices. And I'll show you what they are. You can work them out yourself and see that they all anti-commute. Oh, incidentally, there are many, many different versions, or very, very many different representations of the Dirac matrices. I'll write down what that means in a minute. You pick one and you stick with it. They're all equivalent. They're all absolutely equivalent in the physics. Roughly speaking, the relationship between the different representations, nobody would mind very much if I called the x direction the y direction the z direction, the z direction the x direction. So if I called sigma y, if I just permuted them in some way, they'd be just as good. Same is true of the alpha and beta, the Dirac matrices. There are many, many different representations. We just have to pick one and stick with it. All right, so what are the rules? Once Dirac realized, I don't know what Dirac realized and what he didn't realize, but once in my imagination he realized that he had to go by 4 matrices, he stopped calling these things sigma and called them alpha. Same alpha as up there, except they're not 2 by 2 matrices. He called them alpha. Now, the fact is, I think he wrote this down before he even thought about the one-dimensional case. And now what we need is we need 4 mutually anti-commuting matrices. Alpha squared equals 1, alpha x squared equals 1, alpha y squared equals 1, alpha z squared equals 1. We better also have beta squared equals 1. But then we also have to have alpha x alpha y plus alpha y alpha x equals 0. That's to make sure that when we square this, there's no term with px times py. Similar things to this. But finally, we have to have for all of the alphas, all 3 alphas, we have to have, I'll just call it alpha x times beta plus beta alpha x also equals 0. Same for y and same for z. All right, and as I said, such matrices exist, 4 by 4 matrices.
Can we call beta alpha t?
You could call, you could, but it's not really. They don't form a 4 vector. I'll tell you what forms a 4 vector. I'll tell you in a minute. Once we get there, once we write the Dirac equation, I'll tell you. Okay, here are the matrices. Once you know them, you can forget them because really all it counts is these properties here. You can work just with the abstract algebra. I think you essentially never need the actual form of the matrices. But nevertheless, you just want to make sure there are such matrices. Here's a particular representation. This is not the one that Dirac used. This one is called the Pauli representation of the Dirac matrices. It's not the Pauli. All right, here it is. Alpha, the 3 of them, alpha x, alpha y, and alpha z. I'll explain this notation in a minute. These are 4 by 4 matrices, but they consist of blocks, 2 by 2 blocks. In each block, there's a 2 by 2 matrix. In here, you put sigma, and I'll tell you what that means in a minute. Here you put minus sigma, and here you put 0, and here you put 0. So for example, if I was interested in alpha x, that would be the matrix sigma x up here, minus sigma x down here, 0, 0. And what would that look like? It would be, again, divided into blocks. In this block, put sigma x, which is 1, 1, 0, 0. In this block down here, put 0, minus 1, 0. All others 0. Same thing for alpha y and alpha z. So that gives us and you can check. You can very quickly check that these anti-commute with each other. They anticommute with each other as a consequence of the fact that the sigmas, the Pauli matrices themselves, anticommute with each other. And so as the second you start writing down the products of them, you realize you're just working with the Pauli matrices in some very simple way. They anticommute with each other, and so this kind of thing is satisfied. The only thing we have to figure out is what beta is, and beta is chosen in this representation to just be 0, 1, 1, 0, but each of these are 2 by 2 blocks. So what does this mean? This means in the upper left-hand block here, you put 0, 0, 0, 0, 0. Likewise down here. And what does 1 over here mean? It means the unit matrix, 1, 1, 0, 0, 1, 1, 0, 0. That's beta. I am not going to work out the anticommutator. You know, there's nothing to it other than just multiplying matrices. The anticommutators are 0 of the alphas with beta. And so we actually have a Hamiltonian whose square is p squared plus m squared, the relativistic law of connection between energy and momentum. It sounds good, and it is good.
Quick question.
Yeah.
For the massless particle, you had to make it work and get another degree of freedom, and that was physically manifest in the form of spin.
Actually, it wasn't in there. In the one-dimensional case,
Yeah, the one up right up.
yeah, it's not spin. You can't have spin in one dimension, really. It was a spin-like thing, but it wasn't really spin. Spin requires 3 dimensions to spin around the genuine spin.
So when you added a mass, you had to have another degree of freedom. Is that physically manifested in some other kind of thing? If so, what is it?
It is. It's connected with something called helicity. When we looked at the original equation with sigma here, we found out that if the particle has positive energy, that means that sigma has to be aligned with the momentum here. So there was only one kind of particle with its momentum and spin along the same axis. What we did, in effect here, was to put in another species whose energy is the spin minus the spin times the momentum. So we created another species, doubled everything up, and the other species has what is called the opposite chirality. Chirality meaning the relationship between spin and momentum. If spin is along the direction of momentum, that's called right-handed, like your right hand, your thumb, and your spin. Opposite is left-handed. When we only took the 2 by 2 matrices, we were stuck with particles with only one-handedness. Okay? We put the other one in, we put the other handedness in. That gave us 2 kinds of particles, one which goes this way, one which goes this way, and then we coupled them together by putting this off-diagonal thing here, which mixes the left mover, the left guys and the right guys. The result was a massive particle. This is the sense in which mass for a Dirac particle is a transition or a coupling between the left-handed spinning particles and the right-handed spinning particles.
So massless particles don't have this characteristic of chirality?
No, they have very good chirality. They don't have anything which flips the chirality.
Okay.
Yeah. The massless particles of chirality is conserved.
Okay.
Did anybody understand what I said?
No,
For massless particles, the chirality is conserved. It stays right-handed or it stays left-handed, but the mass term causes transitions between them. It's a term in the Hamiltonian which takes one to the other. How do I know that? Because it's off-diagonal. It takes the upper block to the lower block and mixes them. Okay.
Are these equivalent to quaternions?
These, no, the alpha matrices are not, the sigma matrices are quaternions. Yeah. All right, so since you asked me about quaternions, I'll just spend a moment with them. Quaternions are a way of doing vector algebra. They're connected with the sigma matrices. Let's go back a step. Let's take complex numbers. Every complex number is a plus ib, right? A squared and b squared, right. Every Hermitian 2x2 matrix, every Hermitian 2x2 matrix can be written as a thing proportional to the unit 2x2 matrix plus I times, is there an I? No, I think I misspoke. I think I want to put an I there. Not Hermitian, forget Hermitian. Sigma dot some vector, I don't know, Q, a vector. Everything can be written as a linear combination of, and these things are called, the 2x2 matrices representing things like this are called quaternions, but it's not going to play any role in what we're doing.
So the spin is associated with angular momentum.
Yeah.
And so is there an energy term associated with that?
No, nothing other than this. Now, the alpha here is not actually spin yet. We're going to ask what alpha means physically. What is alpha? Each component, here's something true. Each component of alpha, the three of them, each component is a matrix. It has eigenvalues, and the eigenvalues are +1 and -1, but it has 2 +1 eigenvalues and 2 -1 eigenvalues, because it's a 4x4 matrix. And the question is, what physical quantity is it representing? They don't commute with each other, incidentally, so you can't measure the different components of alpha simultaneously. They don't commute. But you can measure a component. What is the physical meaning of that component? And the physical meaning is very bizarre. It's the velocity. It's the velocity of the particle. The alphas are the velocity, which means to say that the expectation value of alpha in any state is the velocity of the particle. How do you see that? Okay, what you have to remember is you have to go back to the formulas for the time derivatives of the expectation values of operators. I'll just remind you, if I have some operator, let's just call it L, a Hermitian operator, and I'm interested in its expectation value, I won't bother writing in states here, I'll just, some states there, some state. The expectation value of L has a value, and if the state changes with time, the expectation value of L also changes with time. Do you remember the formula for this? It's related to the commutator of the Hamiltonian with L. Now, for the life of me, I can never remember, is it plus I or minus I? No. I don't know, and I'm not going to figure it out. It's not hard to figure out, but I'm not going to bother. We're just going to write I. We can always write I. Doesn't matter. You can write plus I or minus I. But then the question is whether it's commutator of H with L or L with H. And I don't remember. But we're not going to care because it's not important. Okay. The time derivative, and you take the expectation value of this. The expectation value, the time derivative of the expectation value of L, you can just think of that as the average time derivative of L is equal to I times the commutator of H with L. In fact, you can even erase these brackets here and just write it formally, the formal equation that L dot is this. Okay, let's take our Dirac particle and let's consider x dot. X is the x coordinate of the particle. And let's consider, using this formula, let's try to figure out what the velocity operator is. What's the operator which when you measure it, it gives you the velocity? Okay, so this shouldn't be too hard. It's I times the commutator of h, which is what? Alpha dot p plus beta m. That's h, commuting with x. Well, n is just a number. The alphas and betas, they commute with x. They're in a different, they're in a different space. They're not in the x space, they're in this 2x2 or 4x4 space. So beta and alpha commute with x. What's the only thing in here which doesn't commute with x? P. Which component of p? P sub x. So when you work out the commutator, this is not here. Alpha commutes with x, so that means you can take it outside. And you just have commutator with p with x, which is what? Minus I h bar? Okay, so this is equal to minus I times I is plus 1 is equal to alpha, alpha sub x. So alpha, it's a crazy funny theory. The velocity of the particle is not proportional to its momentum. It's given by alpha. So if you want to know what the velocity of the particle is, you measure alpha. Now, it's weird. Can only be plus or minus 1 in any direction. Right. On the other hand, alpha itself is not conserved. If you, oh, that's an interesting question. Alpha itself is not conserved. Why not? Let's see if alpha x is conserved. For that, we have to take the commutator of alpha x, of h with alpha x. Let's take the commutator of h with alpha x. That would be the time derivative of alpha x. And the problem is that h has in it alpha y. Alpha y doesn't commute with alpha x. It also has alpha z in it, which doesn't commute with alpha x. So the answer is that the commutator of alpha x with the Hamiltonian is not 0, which means that the particle accelerates. It does a crazy wobbly motion, which is called Zitterbewegung. Zitterbewegung means something, I don't know, it's some German word meaning drunken Scandinavian, it means. What?
A redundancy.
Right. But of course, what is also true is if you look at the time average of the velocity, the thing is going this way and this way and this way, but the time average is exactly what you expect it to be, namely the momentum divided by the mass, at least if it's moving slowly. But but the main point is alpha is not the spin, it's the velocity. It's a vector quantity, and spin is a axial vector quantity. It's a pseudovector. So I'll tell you what the spin is. It's very easy. Let's see, where is alpha? We erased what alpha is, or did we? No. Here's alpha. Notice it has this minus sigma down there. The real spin is just this. It's a different operator. It's a different operator, very closely related, but it's the spin of, it's the legitimate, genuine spin of the particle. So Dirac discovered a multiplicity of different states of the electron. One of them had to do with the chirality, which way the spin was, or which way the alpha was oriented relative to the momentum. The other had to do with the actual spin of the electron. All right, so
So the Zitterbewegung means a free electron in empty space will migrate back and forth with no external forces. Doesn't that violate something?
no. No.
Well, what about
No. Newton's law says the time derivative of the momentum is 0. It doesn't say the time derivative of the velocity is 0. It says time derivative of the momentum is 0. In most situations, ordinarily, momentum and velocity are related to each other. Here, the velocity of this particle is not the momentum. Weird.
Well, isn't
Now-
velocity c?
No, not when there's a mass. Right.
Relativity, could you think of it as the mass varying as the velocity?
No. In fact, I mean, it's true that in some technical mathematical sense, alpha is the velocity, but it's also true that it itself is not conserved, and so it's going around like crazy in some complicated fashion, and there is a time average of the velocity itself. You can take the time average of the velocity over a little bit of time, and that is the momentum. That is P over m for slow electrons. For slow electrons, it's going around like crazy, doing crazy things, but as it's doing crazy things, it's moving along with a smooth velocity, smooth component of the velocity, which is the momentum. And that you can prove. We won't do that now, but...
Could there be a measurement in which you measure the instantaneous?
Yeah.
And you find it one instant going
Yeah.
one way? And
Yeah. Yes, the answer is yes. Yeah. Right. Okay, now we come to the last thing for tonight. Well, yeah, probably. We come to this strange fact that the Dirac electron can have both positive energy and negative energy. Now, for this purpose, we don't even need to think about the full-blown three-dimensional Dirac equation. It's enough just to study the one-dimensional right-moving electron. Just take that case. We'll come back to the three-dimensional case, but all of the interesting ideas are already there just for the one-dimensional case, and even the one-dimensional case without the alpha matrices, just a pure right-moving massless electron. That already has negative energy. If the particle has positive, let's go back. What was the formula for its energy? The formula for its energy was just H equals P. That's the right, I think that's the right-moving electron, yeah. Not even an alpha. That was our simplest version of the Dirac equation, if you like. It was massless, it only went to the right. Okay? But it has both positive and negative energies, and the reason it has negative energies is because P can be negative. There's no restriction here that P can't be negative. Okay? So we have to figure out, what does this mean, negative energies? Negative energies are very dangerous. The ground state, the vacuum of the world, is not necessarily the state with no particles in it. It's trying to be the state of lowest energy. When you take everything out, when you take all the energy, when you suck out all the energy from the vacuum or from space, what's left is the vacuum. And clearly the vacuum had better be the lowest energy. Otherwise, you could lower the energy past the vacuum, and that's a little bit crazy. And even worse, you could lower the energy indefinitely until you have some sort of monstrous thing with enormously negative energy. What does that mean? The vacuum is supposed to be empty space. There's not supposed to be anything that you can remove from it anymore. No way to lower its energy. So what's going on here? Well, Dirac said, let's take the definition of the vacuum to be the state of lowest energy. What about these negative energy particles? You can put negative energy particles in. If they have negative energy, they lower the energy. So you can lower the energy past zero just by flooding this thing with many, many negative energy particles. Dirac very cleverly said, wait a minute, I know that these particles are fermions. What is the lowest energy state going to be? The lowest energy state is going to be if I fill it up maximally with every possible negative energy particle. Every negative energy particle gives you negative energy, and if you fill it up with every negative energy particle, that's as negative as it can get. Well, wait a minute now. Why can't you put two negative energy particles in the same state because they're fermions. So once you've filled up, see, if they were bosons, you'd have trouble. No matter how many of them you put in, you could always put in more. So if you had bosons, which were negative energy, there really would be no bottom. You could just keep putting them in and putting them in and putting them in, and lower the energy of anything. But Dirac said, wait a minute, if these are fermions, truly fermions, you can only put one into a state. If you fill all the possible negative energy states, then your vacuum is stable because you can't put another negative energy particle in. No room, so to speak. So what Dirac said was the vacuum, if it's to be the lowest energy state, must be the state in which every negative energy state is occupied. And then you can't put any more in. This was a intuitive way to describe some mathematics, which I'll tell you in a moment what the mathematics is. But it's correct. Modern physicists will tell you they don't like that description because it sounds a little, the vacuum is the vacuum, it's not full of stuff. But take it, let's follow Dirac's reasoning because it was very effective. He said, okay, let's fill up all the negative energy states and call that the vacuum. Then what kind of things can this system describe? Okay. Well, we could come along. Here, we'll draw a picture to describe this thing. Let's label. Of course, the momentum is continuous, is a continuous variable, but let's just suppose for a moment that we discretized it. Then here's the energies. Here are all the negative energy levels, lots of them, E. And what Dirac said is fill these all up, put a particle in every one so it becomes a sort of monolithic thing which you can't put any more particles into. And that way you stabilize the vacuum against more negative energy particles. But what do you have left now? So he said, okay, you can certainly put a positive energy particle into this. There's your positive energy electron. But you can do something else. You can remove a negative energy electron from here and put it over here. Take out a negative energy electron from what has become called the dirac sea. The dirac sea, this incredible collection of electrons which fill the vacuum. Remove it, and you have a hole. You have a missing negative energy electron, but you have an extra, let's get rid of this one up here. You have an extra positive energy electron. You've made a hole in the negative energy sea and created an extra positive electron. What is this thing over here? This thing is something. It's a missing, if electrons have negative charge and you plunk one out of the vacuum, you'll be left with a little bit of a hole, and the hole will have positive charge. What about its energy? What will be the energy of this hole here? Yeah, it will be exactly the same as the electron. It won't be negative. Removing a negative energy puts in a positive energy. Okay? Removing a negative energy increases the energy. So by removing a particle from here, you put an extra particle here, but you've also created a negative energy hole, sorry, a positive energy hole in the negative energy sea. And that's called a positron. That's called a positron. Historically, Dirac did not know at first that he was talking about a thing which was identical to the electron, except for the sign of its charge. Why does it have opposite charge? Well, when you fill, because it's a missing negative energy electron. A missing negative energy is the same as a positive energy. So Dirac said this solves his problem. He now has a stable vacuum. There are no negative energy particles. there are only positive energy electrons and positive energy positrons, or positive energy holes. And this then solves the problem. And it does. It does solve the problem. Yeah.
Seems to me the logic is flawed because this picture suggests there will always be equal numbers of electrons and positrons.
Not necessarily. You could start with some excess electrons, or you could start with some holes with no electrons. Not necessarily. If you interpret it by saying you started somehow just with a vacuum, yeah, then it's kind of true, but there's no reason to start with only the vacuum. You could start with some excess of one kind or the other. But let's think about something else for a moment. Okay, so let's start with a vacuum. We start with a vacuum, which means all the negative energy states filled up. And then a photon comes along. Now, think about a photon coming and hitting an atom. It finds an electron and kicks the electron upstairs, right? It kicks it up to higher energy. Same thing will happen here. A photon comes along, whacks an electron. There's no electrons up here, but this thing is full of electrons, full of negative energy electrons. It hits it and takes one of the electrons from here and puts it upstairs, increases its energy. It can't decrease its energy because they're all filled. Okay? All it can do is put it into the upstairs here and leave a hole. Okay, so what's happened? What's happened is a photon has come along and turned itself into a negative energy, a negative charge electron, a positron, and an electron. As a matter of convention, we always draw the electron lines with arrows in them that point up, and positrons with arrows that point down. That's just a convention, but it's kind of a nice convention. It's a nice convention. Okay. Positrons point down, electrons point up, and just remember that whenever you slice this at a moment of time, every particle that you slice with an upgoing arrow is a negative charge because it's an electron, and every particle that you cross that has a downgoing arrow has a positive charge. So this is the Dirac theory of electrons. Let's talk about the field operators describing them. The field operators are built exactly the same way as the boson field operators. Psi, it's built as an integral over the momentum, dp. Creation and annihilation operators for particles of given momentum. Let's take the psi, this one here. That's A minus. The annihilation operator for a particle of momentum p times e to the, I guess it's minus ipx if I'm not mistaken. Yeah, annihilation has e to the minus ipx. Or is it e to the plus ipx? Doesn't matter. Okay, that's the way we built field operators, creation operators and annihilation operators times this sort of thing here. But now these are fermion creation and annihilation operators. They anti-commute with each other. Okay, well, what do we integrate p over? We integrate p from minus infinity to plus infinity. But that means that there are negative energy particles in here because negative energy corresponds to minus momentum, negative momentum. Right? There are negative energy electrons in this formula here, but let's divide it up into two pieces. An integral from 0 to infinity dp, annihilation operator for a positive momentum or a positive energy electron, e to the minus ipx, and another term from minus infinity to 0, dp, creation operator now for a, oh, did I write, I meant annihilation operator, my mistake. Annihilation operator here. Same thing as here. Annihilation operator for a negative momentum particle. Now Dirac said, wait a minute. Actually, I'm not sure who said it. They said, when you're dealing with fermions, the mathematics does not distinguish creation operators from annihilation operators. You can, in the mathematics, say that every annihilation operator is a creation operator. That's because they anticommute. The mathematics just doesn't distinguish them. So instead of calling this an annihilation operator for a negative energy particle, let's just relabel it and call it a creation operator for a positron. What does it do? Remember what it did. It annihilated a negative energy electron. In other words, it created a positron. So let's just call this annihilation operator of a negative energy particle. Let's call it a creation operator for a positron. And he labeled them B's. B's, I don't know why B's, but A's and B's, electrons, positrons. And I think if you work it out and do the a little bit of juggling, you'll get from 0 to infinity again. But you'll get e to the, I think you get e to the plus IPX. Yeah, you do, I think. So Dirac said, you can think of the field operator as a sum of two terms, one with annihilation operators for electrons and the other with creation operators for positrons. I'll give you one example of the kind of thing this does for you. The field operator has two kinds of things. So let's take a process where an electron comes along, emits another electron and a photon. This would be an annihilation operator for an electron. That's an A minus. And a creation operator for another electron, that's an A plus, and a photon operator. Let's call the photon operator A. Okay. You might suspect that where this comes from, and you'd be right, is a term in the Hamiltonian which would be psi dagger of x times psi of x times A. An annihilation operator, a creation operator, and a photon operator. But now if you put in the fact that the operators here have two pieces, one with creation operators of one kind of particle and the other annihilation, and the annihilation operator is the other kind of particle, what you find out is that the same operator has contributions in it, which is not an electron being an electron and becoming a photon, but in fact, for example, an electron annihilating a positron. Electron, positron, photon. If you look around for all the creation and annihilation operators in here, you find that it contains combinations, the same operator which took an electron to an electron and a photon, takes an electron and a positron and makes a photon. So one simple complex of field operators describes many, many processes. There's even another one. An electron and a positron can be created and a photon at the same time, just by using all the various varieties of creation and annihilation operators that would happen in here. This was the start, sort of Feynman diagrams. Of course, it was Feynman who figured out how to evaluate them and make real sense out of them. But Dirac had quite a bit of the structure down. And that brings us, I think, to the end for tonight. So, yeah.
Can you say, how do modern physicists think about this as opposed to using the dirac C?
Very easy. They just say, forget the dirac C, just replace creation operators for negative energy by annihilation operators for positive energy. Just do that flip in the formulas. And when you do that, then it becomes completely symmetric in the electrons and positrons. you discover right away that it's a complete symmetry, so you could think of the vacuum as being filled with negative energy positrons and the holes being electrons, right? Okay, one last thing is that this same pattern turns up in solid state physics. If you have a crystal or anything else for that matter with lots of electrons in it and you want to know what the lowest energy state is, you just put however many electrons you have, you put them into the lowest available states, right? You just, if the ground state is not occupied, you put an electron in there. Of course, they're all positive, but you keep putting electrons in until you fill it up to some level. What level? However many electrons you have, you fill it up. So then you have a ground state, and the ground state is full of electrons. The net charge, of course, is 0 because there are protons there also canceling the charge, so you have a C. It's called the Fermi C. What Fermi had to do with it, I'm not sure. Now you can take an electron out of the C and kick it upstairs to a higher energy state. That leaves a hole. Sure enough, it leaves a hole. Those are called, in solid state physics, they're called holes. But they can also be thought of as positive charged particles. So in solid state physics, you have exactly the same thing. You have electrons, which have energy up above the Fermi level, up above this filled C, and you also have positive charges, which are really this time, just really the missing electrons in the, and of course, the positrons also, not the positrons, the holes also have positive energy because they correspond to a missing energy at a lower energy level. Well, they do have positive energy. So the same pattern is very well known in solid state physics, but Dirac did this first. I always had thought that Dirac patterned this on what happens to electrons in a crystal, until I realized that he did this long before anybody had thought about electrons in crystals. And so, yeah.
I was just wondering if like the Klein-Gordon equation for bosons, does
Yeah.
it have a problem with cascading to the lowest?
No,
thing?
no. No, it doesn't. We don't have time to go through it, but.
Where does spin for boson comes from?
What's that?
Spin for bosons, the spin 1 for bosons. Where do they come from?
Not from this. Not from this. Yeah.
I lost track of when you, in the Dirac equation, when they became fermions. What was it that told you they were fermions?
That it had to be fermions in order to solve this negative energy problem. If without having fermions, you could just keep filling up more and more and more negative energy particles, and the vacuum would just be unstable. You take an atom. The atom can decay, but let's take the ground state of the atom. Why can't the ground state of the atom decay by producing a photon? Well, because there's no energy level of the electron below that. It's got to produce a positive energy photon because there are only positive energy photons. So that means an electron in the lowest energy, it can't decay any further because it's down at the bottom. But suppose there was a whole bunch of negative energy states of the electron. Then no matter how many of them you filled up, you could always add another one to the negative energy states and have the atom decay by having the electrons sink down even lower. What prevents that? What prevents that is the electrons are already there, but it can only prevent it if they're fermions.
Well, was there, presumably there's a Dirac equation for bosons.
It's not a Dirac equation. It's a Klein-Gordon equation, which is different and does not have the form H is equal to a linear function of P. It's a more complicated. Right, so you can look up now the Klein-Gordon equation for bosons. We just don't have time for it now. But I think you're probably in a good position to follow it. And it's a very different structure, a very different structure. Doesn't have Dirac matrices, doesn't,
From the last part you're saying, it appears that the radiation operator for an electron is equivalent to the annihilation operator of a positron, but not quite.
Negative energy positron.
But there's a difference, and that they're not quite the same. There's, which applies to me, a degree of freedom, another degree of freedom, which would be charge.
Yeah,
Accurate?
yeah.
If-
Well, it's not really a degree of freedom. Every electron has a negative charge. Every positron has a positive charge. But yeah. Okay, one way of thinking about it, it's sort of semi-correct, but one way of thinking about it is these 4x4 matrices, there are two binary things going on. One binary thing is a spin, and the other binary thing is whether it's an electron or a positron. Now that's not quite right, but it's a reasonable counting of how many different states you have. Right.
Won't the infinite dirac cause an infinite cosmological constant?
There you go. Yeah. Right. And right. You can either think of it as the energy in the Dirac sea, but you can also just think of it as the 0-point oscillation of the fields. Photons you don't usually think of as filling up a Dirac sea, but they also contribute vacuum energy. A half h bar omega for every oscillating mode of the electromagnetic field, and that's also infinite. Now, it is true that for the photons and for bosons in general, a curious fact is that for photons, the vacuum energy is positive. For fermions, it's always negative. So you could imagine canceling them, and, but unfortunately, they don't really cancel because the electron has a mass, the photon doesn't have a mass, and you're always left over with some huge amount of vacuum energy. Right, so you're right. That's right, but keep in mind the only time that the 0 point of energy comes into anything is when that energy is gravitating. For all other purposes, the 0 point of energy can just be subtracted off and neglected because it doesn't come into any energy differences. It's only when you say, wait a minute, energy gravitates that you have to worry about it. Okay, yeah, one more.
Can you say more about how mass relates to left and right moving? That seems...
It's just a term in the Hamiltonian which switches from one to the other. That's all I can say. And you can if you like to try to picture it, you can try to picture it, but it's always, these pictures are always defective. So I won't say any more. If I had more to say, I would have said it. Right. Okay.
For more, please visit us at stanford.edu.